Let's say you're ordering a pizza and you're about to get the large 18-inch pizza when you realize that for the same price you can get two medium 12-inch pizzas. That's a better deal, right? Not at all. So the area of a circle is pi r squared. In this case, 18 and 12 are diameters, so we have to half them to get the radii 9 and 6. So the area of the large pizza would be 9 squared times pi, or 81 pi, and the medium 36 pi. So two mediums would thus have a combined area of 72 pi, which is a smaller area, meaning less pizza. But kind, 12 times 2 is 24, which is larger than 18. But we really shouldn't compare the diameters this way, because the area is really what tells you how much pizza you're getting. And the area formula squares the radius, so a couple of inches difference in the radius or diameter translates to a much larger difference in area because of how it gets squared. In most cases, but not all, the largest pizza is almost always the best deal. Riddle of the day. Say that there's a 10% chance of rain on any given day, independent of all other days. If it rains today, what day is the most likely to be the next time that it rains? Pause here and give it some thought. So the answer is surprisingly tomorrow. The chance that tomorrow is the next time you see rain is simply the same as the chance of it raining at all tomorrow, which is 10%. If we want it for the day after tomorrow to be the next time it rains, that means it can't rain at all tomorrow. So we have to multiply the probability of no rain tomorrow times rain the next day for 9%. For the day after that to be the next rainfall, that means we have to have no rain for 2 consecutive days. So we have to multiply these 3 probabilities to get 8.1%, and it just keeps shrinking day after day. The key is that I did not ask what day is it most likely to rain. I asked what day is it most likely to be the next rain. Just imagine you had to wait an entire year for the next rainfall. You'd be very unlucky. So that's why it makes sense for the probabilities to keep shrinking as time goes on. Riddle of the day. Can you spot the problem in this picture? Okay, politics aside, this is only a math question, so pause here and think about it. Okay, how do gears work? On a very elementary level, say these are the teeth of the gear. If a gear is turning clockwise, any gear that it's attached to is going to turn counterclockwise, or just in the opposite direction. So in this diagram, let's say between the Canada and Mexico gear, one of them's clockwise, the other's counterclockwise, then which way is the USA gear turning? It can't be opposite to both of them. The system would just be jammed. Numberphile has a good video showing how 3 gears can work in 3 dimensions, but on a flat plane, any odd number of gears that are all connected in a loop will not work. And yet artists still like to draw it that way. Probably they don't know. Have you ever heard that in a room full of 23 people, there's a 50% chance that 2 of them will share the same birthday? But aren't there so many possible birthdays and so few people? When calculating a probability, it's often easier to work out the opposite scenario. So let's start off with the probability that you and I have 2 different birthdays. So I can have any of the 365 birthdays I want, and you have to have any of the other 364, giving us a probability of 99.7. If there's a third person, they'll have to choose among the 363 leftover birthdays, and a fourth person will have to choose among any of the 362. Do this with 23 people, and the probability that we all have unique birthdays is around 50%, meaning the opposite scenario, that there's some overlap somewhere, is the other 50%. The reason why is because even though there's a very low probability of any 2 people sharing the same birthday, there are so many pairs of people we can match up and compare in that room, much more than just 23. You've probably heard your teachers tell you at some point that you can't divide by 0. Have you ever wondered why that is? The thing is, we could allow it. But 0 times any number equals 0. So 0 times 2 equals 0, which also is the same as 0 times 1. If I was allowed to divide both sides by 0, I could show that 2 equals 1. And I could also show that every number equals every other number this way. $10 would mean the same thing as $0, and negative $20, and $1 million, and numbers would just lose their meaning. When you divide something like 10 by 5, you're essentially saying, how many times do I have to subtract 5 away from 10 in order to get down to 0? But 10 divided by 0, even after infinite subtractions of 0, you'd still be left with 10. So even infinity is not a good answer. Division just doesn't work that way. If we want numbers to be useful and for math to be meaningful and consistent, we have to set up some rules on how numbers and operations work, and not dividing by 0 is one of those rules. Riddle of the day. Let's say that we have a class of 10 students and the teacher has promised them that if they get a class average of an 80 on an upcoming test, then they get a pizza party. The first 9 tests have an average of 78. How high does the 10th student need to score on their test in order to bring the class average up to an 80? Pause here and think about it. We don't actually know the exact scores of the first 9 students. We only know their average, but it turns out that's enough. The sum of all the first 9 test scores divided by the number of tests is the average, and that's 78. That means the sum of the first 9 test scores is 78 times 9, which is 702. If we want the entire class average to be an 80, well, that would be the sum of all 10 test scores divided by 10 equaling 80. Now we know the sum of all 10 test scores has to be 80 times 10, which is 800. However, we already know the sum of the first 9, 702. So now we have an equation, 702 plus the 10th test score equals 800. So the 10th student has to get a 98 or better in order to bring the class average up to an 80. Riddle of the day. So Achilles is racing against a tortoise and he gives the tortoise a head start. When it's his time to go, it'll take him some time to catch up to the tortoise, but by the time he reaches that point, the tortoise will have moved forward a little bit. And in the time that it takes Achilles to catch up to that point, the tortoise will have another chance to move forward even more and maintain its lead. By that logic, the tortoise will always maintain a lead and Achilles will never catch up to it. But how is that possible? So this paradox takes us back to ancient Greece with Zeno of Elea, who believed that this proved that all motion was simply an illusion. But of course Achilles can run. He can outrun the tortoise and in a finite period of time. The fact that you can divide a finite period of time and a finite distance into infinite segments is no contradiction. Take half of a pie and then add a quarter and then add an eighth and then a 16th. Each time you're adding half of the remaining empty space. Then you'll have yourself an infinite sum of numbers all greater than 0, but still all adding up to 1. Would you believe that there are at least 2 people in Toronto who have the exact same number of hair follicles on their head? This is due to the pigeonhole principle. Say that you have 10 pigeons and 9 holes for them to fly into. There aren't enough holes for every pigeon to have a different one, so there has to at least be one hole with more than one pigeon in it. Well, a person has an average of 100,000 hair follicles on their head. Let's say for the sake of argument, if some people have really super thick hair, the most a person can have is 1 million. So assign everyone in Toronto a whole number between 0 and 1 million, which is the exact number of hair follicles on their head, and there will be fewer options for people to have than there are people in Toronto, which has a population of 2.9 million. Not enough for everybody to have a different number, meaning there has to at least be 2 people with the exact same number, and they don't even know it. Riddle of the day. I've got an 8x8 chessboard here and a rook here at this top corner. Is it possible for my rook to make it all the way to the opposite corner by touching every single square on the chessboard once and only once? Pause here and think about it. So this is actually impossible. First of all, we have 64 squares on the chessboard and I'm already starting out on one, so I need to touch all 63 others in 63 moves, where my last move lands me on the desired spot. However, if you're on a white square, your only possible moves are to one of the black squares around you and vice versa. If you're on a black square, your next move has to be to a white square. However, I'm starting out on a white square, so my first move has to be to one of these 2 black squares. And then my second move is going to have to be to a white square. My third move, a black square, fourth, white. And I'm always going to land on black squares on odd-numbered moves and white squares on even-numbered moves. But my 63rd move has to land me on this white square, and that's impossible. Riddle of the day. Here's a bit of a tough one. Let's say that I've got 25 horses and I need to find out which are the top 3 fastest. Problem is, I don't have a stopwatch or any tool to time them. All I have is a racetrack that I can race them on and compare them against each other. And the racetrack only holds 5 horses at a time. What is the minimum number of races that you need to hold in order to find the top 3 fastest horses? Pause here and give it a try. First up, we need to race everyone in random groups of 5. And let's say that the columns represent the order they placed in their race. Anyone who came 4th or 5th in their race is automatically out of the running. Now race everyone who came first, and let's say the results of that race are A, F, K, P, U. Horse A is for sure number 1, but we need another race for 2nd and 3rd because B or C could possibly outrun F or K, for instance. P and U are out of the running, along with everyone they beat. K can hope for 3rd place at best, so everyone who lost to him is out of the running. And similarly, F and G can only hope for 2nd and 3rd. This leaves us with 5 more horses in the running who will race for 2nd and 3rd place to A. Okay, why is every number raised to the power of 0 equal to 1? Think about it this way. 2 to the power of 1 is 2, and as I increase the exponent by 1, I multiply by 2 every time. So 2 times 2 is 4, times another 2 is 8, times another 2 is 16. So going backwards, I'm dividing by 2 every time. So as the exponent goes down by 1, I'm dividing by 2. So 16 divided by 2 is 8, divided by 2 is 4, divided by 2 is 2. If I divide by 2 one more step and bring the exponent from 0 down to 1, 2 divided by 2, well, that's equal to 1. I know it can be confusing because you learn exponents as a number multiplied by itself that many times, but there are many ways we can apply exponents beyond just positive whole numbers. So we can even say 2 to the power of negative 1 is equal to 1 divided by 2. So all I have to do is divide by 2 one more time, and that's 1/2. Riddle of the day. Let's say that I've got 100 light bulbs all lined up in a row, switched off, and 100 people to take turns hitting the switches. The first person hits every single switch, second person hits every second switch, third person every third switch, and so on. After the 100th person hits the 100th switch, how many switches are left on? Pause here and think about it. Okay, let's take, for example, light bulb number 10. It starts off and it's switched on by person number 1, off by person 2, on again by person 5, and off again by person 10, after which point nobody ever touches it again. So the switch is hit by person number 1, 2, 5, and 10, which are the 4 factors of 10. It starts in the off position, and if it's hit an even number of times, it will stay off. So if it's hit an odd number of times, it will stay on. So the number has to have an odd number of factors, like 1, 4, 9. These are all perfect squares. So the answer to the question, how many light bulbs in the end stay on, is the same as how many numbers between 1 and 100 are perfect squares, and the answer is 10.